Hello, everyone, and welcome to this webinar hosted by Lumex Instruments. I hope you're all doing well, and I'm very happy to see everyone in here. And today we are going to talk about how fun it is to develop a method using capillary electrophoresis on a topic that's pretty hot today. It's a topic about cannabis, and we're going to talk about a method development for detecting 14 cannabinoids by capillary electrophoresis. You will notice that your microphones and your cameras have been disabled for now, but we promise to enable them for you once we reach a question period. So the question period will be at the end of the webinar. So a few guidelines is that what I recommend you do is to write your questions down so that at least we know that you have a question and then you don't forget it while we're doing the presentation. And once we reach the question period, we will, again, as I mentioned, enable you to ask your question. This presentation for our guest speaker will take about 30 minutes. And of course, any observations or comments are welcome. And of course, they can be emitted at the question period. So our agenda for today is I'm going to start talking about Lumex Instruments, what it is that we do, our activities, our applications. We're going to take a quick look at our instrument portfolio, where we can help you answer any analytical tasks. And then we will jump in right into the subject matter, which will be our featured guest presentation. After that, the question period will follow. All right. So we'll start with Lumex Instruments. We have sold way over 1,500 instruments in 92 countries. We have several offices around the world. The office in North America is located near Vancouver. It is in Mission, British Columbia. So any North American support would be done through that office, which I am part of. Our scope of activities, we have, we are an instrument manufacturer company, but with instruments, we understand that we need to develop applications. So sometimes, like we're doing right now, we're talking to scientists that will enable us to develop some applications. Other times, we will develop applications on our own as well, because we do also have scientists that are able to develop applications. We are responsible for everything that we manufacture to train and install in your laboratory. And because we have multiple offices around the world, we are able to support you service-wise around the world. Our applications are numerous. We actually are involved in environmental protection, anything that deals with water management. We're involved in that. Food and testing and agriculture, oil and gas industry, the chemical industry as well. We're involved in that too. Geochemistry and mining. We also even are involved in geology surveys, believe it or not, which is kind of cool. This is a new place where we're involved in, and we are now moving into life sciences and pharmaceuticals. Let's talk a little bit about our instrument portfolio. So I'm going to start off with this first instrument here. This is our mercury analyzer called the RA915M. It's our most versatile mercury analyzers because it can actually do, with the right attachments, gases, liquids, and solids. So if you have a need for any mercury detection, this would be the instrument of choice. We do also have other types of instruments for mercury analyzers, and if you need more information on that, we'll be more than happy to share that with you. The next instrument that I'm showing you is our fluorometer called the Fluorat. It's the 4 and 5M, and these two can actually do several applications. The most, say, popular application would be TPH, total petroleum hydrocarbons. And we also have chemical on demand, vitamin B, and turbidity. So a very wide mix of applications with that fluorometer. What's neat about this instrument is it is a portable instrument. It can be used as is or can be used connected to a computer through the software. Our next instrument that you're seeing here is part of a FTIR, NIR families of instruments. This is our NIR FT12, which is widely used in agriculture, anything that involves wheat, so bakeries, pastas. We actually use this to determine the percentage of protein, fat, moisture, ash. We're also involved in milk products, and we are moving into the meat product world with this particular instrument. What's cool about this instrument is that you put your sample in a cell, you load it in, you press go, and you get your answer in 90 seconds. I wish that would be so easy like that in CE, but unfortunately, we're not quite there yet. The next instrument that you see here is our FTIR FT08 instrument. And this instrument actually is pretty neat for its feature because it has a very large sample compartment. The reason why this is a nice feature, it's because you can actually put a microscope in there and do some microscopic FTIR, which is kind of a cool technique to do. But typically this FTIR would be used for transmission analysis. So anything for identification. It can be also coupled to an attenuated total reflectance ATR component as well, where now you could do quantitation also in the FTIR. The last instrument that I wanted to show you here in our instrument portfolio before I actually deep dive into two more instruments that are a little bit more related to cannabis. This particular instrument is our atomic absorption spectrometer. It's a graphite furnace atomic absorption spectrometer called the MGA 1000. And with this guy, of course, we can do all sorts of elements, being macro elements such as sodium, calcium, potassium, magnesium. We can also do smaller elements as indicated here. So we can do aluminum, beryllium, cadmium, name it. It can do several types of elements. It's got several Tourette positions to be able to do multiple elements at one time. Now, diving into a little bit more into the cannabis testing instruments, because we're going to be talking about cannabis and cannabinoids today, I wanted to chat a little bit about the capillary electrophoresis, or CAPEL 205 system, which is the system that was used to produce the paper that our guest speaker is going to talk about. And this system is an open platform, which means that you can actually do any type of capillary electrophoresis analysis in this system, provided that what you're trying to analyze has a residual charge. So we've done several works with, as you can see here, of course, we're going to talk about cannabinoids, but we're also going to talk about, we've also done organic acids in wines. We've done anions and cations in all sorts of beverages, and also water testing as well, amino acids in feeds, nutrient testings in fertilizers, which would also be an anionic or cationic type of analysis. It's basically very versatile. It can be used to do several types of buffer analysis within one go. So as you can see, this instrument can actually serve as a good method development instrument and can also serve as a QC type instrument. And the next instrument I wanted to talk to you about is our Ariana real-time PCR. And this one's actually particularly important for people in the cannabis world that are actually growing plants, as this guy can actually detect the pathogens that could affect the biosafety of your plants. So we actually have developed a chip where we can do 14 analysis of samples, and they can actually be detected in 35 minutes which is really, really cool. It kind of gives you a really quick answer as to if there's some pathogens that would be present. So that's pretty much where this system lies. And if you need more information about this, please feel free to contact us as well. All right. So now we're actually going to move into our subject matter today. So I'd like to present to you Emil Zaripov. So Emil actually has done his BSc in biology at York University in Toronto, where he worked in investigating protein structures using NMR spectroscopy. His undergraduate research focused on studying the binding of the HAC1 protein to the protein PIRB. He then started his PhD program in biology at the University of Ottawa, where he is right now, under the supervision of Dr. Maxime Berezovsky. Emil's doctoral research focuses on the broad applications of capillary electrophoresis for bioanalytical chemistry. One of his notable projects utilized capillary zone electrophoresis, so CZE, on a Lumex 205 capillary instrument to separate and analyze 14 different cannabinoids. This work was published on a peer-reviewed journal a few years ago. So, Emil, please share with us your findings. Thank you.
Hello, everyone. So I hope this is visible right now. Let me jump back to this slide number 1. So thank you for the introduction, Patrick. I would like to present to you today the single run separation and quantification of 14 cannabinoids using capillary electrophoresis, or capillary zone electrophoresis. So first, I'd like to give a little introduction why we did this with our supervisor. So as some of you may recall, or all of you, in 2018, Health Canada legalized adult access to recreational cannabis in Canada. Meanwhile, even though it's legalized, companies are still required to provide the information on the contents of their products, which means they need to report the concentration of THC and CBD at the same time. Now there's THC, that is the psychoactive form, and that is THCA, which is acidic form produced in plants. These compounds are actually reported together as a total THC content, which means THC plus THCA. For CBD, it's the same procedure where they report CBD and CBDA combined as a total CBD content. They may do the separate quantification as well, but that's how they're mostly doing it. And the reason for that is because upon consumption, the acidic forms actually get converted to decarboxylated forms, and at the end, concentration of these two compounds together defines the product. So every company must provide that information. So we wanted to develop a method how to quantify them and for the companies to use. So I would like to give a little bit of background on how cannabinoids are produced in the plant. This is very simplified and it doesn't touch the mechanisms in depth, but it gives you the precursors and the two major pathways of how cannabinoids are synthesized in the plant. So the two precursors are, one of them is a common precursor for both pathways, is geranyl pyrophosphate. And the second precursor is either divarenolic acid or oleftolic acid. Now, the difference between those two is just in the side chain, where in divarenolic acid it's 3 carbons and in oleftolic acid it's 5 carbons. Other than that, the pathways are exactly identical, and in both pathways they're first producing CBGVA or CBGA, depending on which precursor is used. Every downstream pathway of these compounds is identical aside from that side chain. So I want to first go through the oleftolic acid pathway for a reason that is more commonly known to people on average. So oleftolic acid and geranyl pyrophosphate would produce the CBGA compound, which is a precursor to everything else. So CBGA can then be converted to either THCA, CBDA, CBCA, and then THCA in its turn can also be converted into CBNA. Now for diverinolic, it's the same. They look the same, but there is a nomenclature that requires to put V, which is coming from diverinolic acid. So V comes from there. So the compounds would be CBGVA, which can be converted to either THCVA, CBCVA, and CBDVA. Please note that all of these compounds are carboxylated. So they have carboxyl group, and that's how they're biosynthesized in the plant. These forms of the compounds are considered not psychoactive. So we're profiling 14 cannabinoids. 7 out of those are acidic forms, highlighted by red here, which are synthesized in the plant, and I labeled them as untreated. So I highlighted the carboxyl group, so they all have the carboxyl group and are acidic. Upon heat treatment during consumption or the product preparation for edibles or for vaporizing products, the compounds are converted with heat to decarboxylated versions. So for instance, THCA would be converted to THC and CBDA would be converted to CBD and so on and so forth. And these compounds, THC and CBD, are commonly known for their psychoactive properties. And going back to the requirement for a declaration of the concentrations, as I said, total THC content is required, which implies THCA plus THC, because it's assumed that during consumption, THCA will be completely converted to THC, which is all you need to report. So this constitutes the 14 cannabinoids that we separated, and I'm presenting right now to you. So I wanted to find out if there was any work using CE separating cannabinoids prior to my work, and turns out there wasn't a lot. So there was a publication from 2002 that separated CBD, THC, CBN, and THCA. So that is the first paper that I could find. The second one was from 2012. It separated THC and CBD, and the rest numbered compounds, as you can see in the middle, they're just synthetic cannabinoids. So they're not naturally occurring cannabinoids. So they separated THC and CBD in this method. And then the third method is in 2015, they separated THC and CBD. And the peak 3, if I recall correctly, it's an internal standard. So there was not a lot of papers separating the compounds because predominantly the field was full of LC methods as opposed to CE. So we decided to fill in that niche, and we published a paper in MDPI separations and titled Single Run Separation and Quantification of 14 Cannabinoids Using Capillary Electrophoresis. Now, as Patrick already introduced the instrument, it was done on Lumex Capillary 205, and our BGE, background electrolyte, was actually quite simple, and it was 6.5 millimolar sodium hydroxide with 25 micromolar beta cyclodextrin concentration, and all of that was diluted in 60% acetonitrile. Acetonitrile serves the purpose of solubility for cannabinoids. As they're quite oily, they don't like to separate in pure aqueous BGEs. We injected the sample at 12 millibars for 3 seconds and applied 450 volts per centimeter electric field. Our capillary was 60 centimeters in length, and internal diameter was 75 microns. So it's a typical capillary employed in CE analysis. We detected all of our compounds with UV absorbance at 230 nanometers. So first, for method development, we had to do it with the standards. So originally we ordered 14 standards individually, and at the same time we made a mix of them. And this is how the mixture of 14 cannabinoids at equal concentration of each looks with our method. So we can see that all of them separate to the baseline aside of CBG and THC, where is a little bit overlap that it doesn't reach the baseline. However, they're very easy to quantify. This overlap is very small, and the quantification does not pose any issues. So in blue, I highlighted the decarboxylated versions that are converted from the acidified versions by heat, and the red ones then are acidified versions. Please note that because they're acidic, they take the red acidified versions take longer to migrate because of the higher presence of negative charge coming from carboxylic acid group. So they're quite easy to separate into two blocks, where first it's all of the decarboxylated versions migrate, and then followed by all of the acidified. So the separation is quite good. So we constructed calibration curve for each of the compounds to quantify them, to be able to use this method for further quantification with the real sample. All of our compounds fall, all of our calibration curves fall within linear range between, I believe it was 2 micrograms per milliliter to 50 micrograms per milliliter. So they all fall within that range. I want to give you a little bit of information of the limit of detection and quantification. So I provided here LODs and LOQs in both in liquid form, so in solution, extracted solution, as well as in the dry plant. Because we work with the dry plant and we want to extract dry plant to quantify, we want to be able to see how our method works in for plant material. So first, I want to give you information on the liquid limits of detection and quantification. So they're all in the range for LOD, they're all in the range of between 1 and 2 micrograms per milliliter, and our LOQs are within range of 3 to about 5 to 6 micrograms per milliliter. Now, how the dry mass was calculated? Well, because we extracted the dry material in methanol, we assumed 10-to-1 ratio of extraction solvent to plant material. So one gram of plant material was extracted with 10 milliliters of methanol, giving us 10-to-1 ratio. So I did some literature search on what's the expected concentrations of the each compound in actual plant in different strains. And this is just a rough summary on the right-hand side of the table of what we're expecting. And for all of them, we're expecting the range of milligrams of compound per gram of the plant, aside from CBDV and THCV, where it's a sub milligram per gram. So it's around between 0 and 1,000 micrograms per gram. For everything else, it falls within the range of our limit of detection. And our limit of detection is actually in the range of tens of micrograms per gram. So that would be about, if I understand it correctly, it would be about 100 times less than what is expected in the plant. Aside from the cases where the plant just doesn't contain this or this cannabinoid, which can be in the case of CBDV or THCV or even CBG, where it can just be 0 and then we wouldn't detect it. But within the expected range, our method should be able to very well quantify and detect them if they're present. I did a lot of injections of standards before I proceeded with the samples to determine the precision. And while the precision is below 10%, between concentrations of 20 micrograms per milliliter and 50 micrograms. Below that, the precision starts to drop. And I don't have a good explanation for this. It's an empirical evidence that I'm having. I assume that it's a combination of different effects. One of them could be, in my opinion, adsorption to capillary wall, because it's very prominent at low concentrations. So if we want to work with this method, I would propose to work in concentrations above 20 micrograms per milliliter. But the good thing about that is that is still going to be within the limit of detection and quantification for the plant. So it would not be an issue for the real material analysis. For last bit of the method development is the addition of beta-cyclodextrin. So normally beta-cyclodextrin is added as a chiral selector and to assist in additional separation of the compounds. But in our case, beta-cyclodextrin did not affect separation at all. But what it did is significantly shortened the runs. So without cyclodextrin, CBGA, which is the last compound, migrated, sorry, around 29 to 30 minutes. But with beta-cyclodextrin, it migrates around 17 minutes. So we get a significant shortening of the migration time if we use the beta-cyclodextrin. But if we don't want to use it, we can just do it with the naked BGE. The separation would be identical. It's just the runs that will be longer. Then if you want to deal with that, you could do it without beta-cyclodextrin. Just to include, we wanted to do some LC separation. It's not as well characterized as our CE method, but we did LC nonetheless with the help of Professor Corey Harris that provided us with the samples and guidance on cannabis. So in his lab, we developed a method that separates 14 cannabinoids with quite good resolution in about similar time, because our method was migrating everything in under 20 minutes. So is this method. So the time is quite equivalent. But there is some overlaps, there's more overlaps between the peaks, and not all of them separate to the baseline as they do with the CE. In addition, there is a baseline drift that may make the quantification more challenging, although we can go around it and still perform the quantification. After all of this, we developed the method with the standards. We wanted to profile the actual plant material because we want to validate the method on a real sample. So we obtained the plant from Dr. Harris's lab, just a dry plant, and we ground it up to powder. The powder was then baked at 120 degrees for 20 minutes, and that is to ensure a degree of decarboxylation. So we don't just detect THCA and CBDA and all the acidic forms, but we also detect the decarboxylated form. That plant material was extracted with methanol and filtered using syringe filters. And then just as is, without any concentration or evaporations, it was injected in CE and analyzed. So the protocol is quite simple and will take no longer than 30 minutes, including the heat treatment time. Here's in this slide, there's 2 electropherograms, and first one is standards, our 14 standards that we used to develop the method. And on the bottom is the sample, the real sample that we extracted. As you can see, the most prominent compounds are THCA and CBDA, which is expected with the literature. Almost all literature agrees on the consensus that THCA and CBDA will be the most dominant compounds, followed by THC and CBD around 6 minutes, THC and CBD, which are lower but are still present. So our heat treatment method, decarboxylation method, is working and effective, but it doesn't fully convert. If you want to detect just CBD and just THC, longer heat treatment is required, and all of these compounds will be converted to a non-acidic form. So here we can see all of the compounds except the CBDV and THCV. So the variants of the cannabinoids are just not present in this strain. Maybe they're present in lower concentrations and below limit of detection. I would assume they're either absent or below limit of detection. Regarding CBC migrated as a very small peak, as you can see, it's labeled here. It's very small, but it was high enough to quantify and to detect. So it's above LOD and LOQ, and CBC was detected reliably with our method. We performed the quantification of each of the cannabinoid in the plant and reported that as milligrams per gram of dry cannabis. And our highest concentration was CBDA, followed by THCA. Then you can see highlighted in blue there decarboxylated form CBD and THC. And to my surprise, there was also CBGA that was present in quite high concentration. And because that's a precursor, I assumed that it would be converted later on to different compounds because it's the first step in the biosynthesis pathway. As you can see, we don't have any variants, THCV, CBDV, THCVA, CBDV. As I said, we could not detect them in this particular strain. While method performs well and separates that, there are some significant drawbacks on this method. First of all, BGE is not buffered. It's just sodium hydroxide in 60% acetonitrile. So pH can fluctuate. During electrophoresis, it can drastically change the pH because of the migration of ions. Additionally, because it's acetonitrile and 60% acetonitrile, BGE can evaporate. And that would also increase concentration of electrolyte and at the same time increase pH and decrease solubility of cannabinoids because the acetonitrile would fly away. So the third drawback is sodium hydroxide concentration must be very precise. As you can see, while in this method 6.5 millimolar sodium hydroxide, everything separates. If the concentration of sodium hydroxide is below 6 millimolar, CBG and THC lose their separation. And above 7 millimolar of NaOH, CBN and CBC lose their separation. So the method has very narrow range of effectiveness when it separates. And you must prepare all the buffers fresh because otherwise they will evaporate, and you can't use one buffer vial for more than one separation, or you lose precision and separation. So it's quite intensive to work with, but time intensive and labor intensive, but it does separate the compounds well. For the future directions, given that I have more experience in analytical chemistry now in CE, I would absolutely use a different electrolyte providing similar pH, but I would want to have buffering capacity. So I would most definitely first electrolyte that I would look at is triethylamine acetate, which can buffer around 10.8 pH. So I can easily do 11 point, low 11 point something pH to enable my separation, and at the same time buffer. So in case of a mild evaporation of acetonitrile, my pH should not adjust that much and preserve the separation. Additionally, while we're looking at 14 cannabinoids, it's not a small number, but the natural diversity of cannabinoids is broader than this. In certain strains, we might encounter cannabinoids that are not part of this list, but they might migrate around the same time and not separate in our method. So we need to investigate this using a more sensitive platform such as CEMS to see if certain cannabinoids, different cannabinoids co-migrate within one time frame. Luckily, Capillary 205 can be connected to a mass spectrometer, which was done in our lab as well. We could, I didn't do this, I didn't get to do this, but that would be an interesting thing to do, to profile them with CEMS for the future. So for my acknowledgements, I want to thank, first of all, Berezovsky Lab Group, my supervisor, Maxim Berezovsky, on the right on the picture. I want to thank Yuchu, he's my lab mate and my friend, who helped me with the sample preparation, and all the bench work was assisted by him, for which is I thank him. Also, Harris Lab Group, Corey Harris, primary investigator, who provided us the guidance on cannabis, on legislation, who gave us the samples, as well as TLE for data analysis and sample preparation, his student. And lastly, Lumex Instruments itself for providing us the instruments and funding, and for development of the instrument. So that wraps it up. Thank you very much for listening, and I would like to take some questions if you have any right now.
All right, everyone. Thank you so much, Emil, for this great presentation. everyone now, your microphones and your videos have been enabled. So if you do have a question for Emil, please just go ahead and raise your hand. You probably can use the icons, or just go ahead and verbalize your question when you're ready. Yeah, go ahead, Karen.
Hi, Patrick. Hi, Emil. Really, really nice presentation and nice work. So congratulations on that. I had looked briefly at the article, but not in big detail. Thank you for the frank discussion of the sodium hydroxide buffer. That was one of my questions, and it's interesting. You need a narrow range. Did you? I guess my question is, since it's not a buffer, it's an electrolyte, and you alluded to buffer depletion. How did you have to put fresh buffer for every run?
Absolutely.
Yeah. Okay.
Yeah, it would, the separation would be lost. Like if I inject in the second vial, the same vial twice, it's gonna lose the separation.
Okay, so that's what you meant. It was like not even more than one injection, you know, like most people change after maybe 5, but that's it. One separation for 15 minutes or whatever is enough to change the pH.
Yeah.
And just one more question so I can let somebody else ask, because I have several. Did you, and I appreciate 40% acetonitrile is quite a bit, so of course it's going to evaporate. Was that added just to get the high enough concentration of beta-cyclodextrin? Because I know beta-cyclodextrin only has a solubility of 18 millimolar, and you have like something quite a bit higher, 25. Is that the only reason acetonitrile is there, or is it for the solubility of the compounds as well?
It's for the solubility of cannabinoids. They don't like being in water, so it's for cannabinoids. And regarding cyclodextrin, yes, solubility in water, I believe, is lower than that. But if I recall correctly, because it was done a couple of years ago, the way to dissolve it would be in ammonia, basically in high pH. So I think it's better at solubilizing at high pH, which is our buffer, pH of 11.6, I believe. So it dissolves quite well there.
And so, and you don't, at that pH, you're not deprotonating any of the alcohol groups, like any of the OH groups on the cyclodextrin?
I don't believe so.
No, I think it's 14.
Yeah,
Over
I don't believe
14, Karen,
anything.
would be the alcohols. Yeah.
Yeah. Okay. So you're below the pKa of those. Yeah. Maybe they don't have a good. Okay. Thank you.
Mm-hmm. Someone was raising hand, but I don't remember who that was.
I think this would be Vadim. Hi, Vadim.
Yeah.
Hello.
Yeah. Hi, Patrick. Hi, and thank you very much for this very nice presentation. Thank you. I think it will help us all to promote the instrument as well. I have just 2 short questions as a experienced user in capillary electrophoresis. First question, do I understand correctly that if we take the sample solution, which is just ready for the injection, it is 100% methanol?
Yeah.
Nothing more. It is just methanol.
It's just methanol. That's right.
And when you inject the methanol by pressure, you also make some notes about the precision, the accuracy of the analysis. And what about the reproducibility in terms of milligrams per liter, actually? If you inject from the 100% of methanol, didn't you see that there might be any fluctuations in this case because of this methanol? No?
Absolutely. Methanol does cause issues for me when injecting, not just in this project, but any injection from organic solvent gave me certain issues in CE. And with this, what I believe I did was I injected with a certain, basically, if I do low pressure and low time, it would be a lot less reproducible. But I think I'm injecting plug large enough that it's quite reproducible. But yes, I did encounter a lot of issues with injection. At first, I thought it was some incompatibility with my electrolyte or something is precipitating inside. It was the issue of methanol, because when I didn't do any injection, my system blank performed very well. And then with the injection of methanol, it did cause issues. I think I overcame it by injecting longer plug in our case, and it was fine, working fine for me.
Longer plug, you mean this 3 seconds for 30 millibars? Yeah.
For 10 millibars, yeah.
10, yeah. Oh, okay. Thank you. Another question. You mentioned that, well, it's obvious that the background electrolyte does not have buffer capacity. That's clear. And in order to overcome the problem, you suggest to use for each run the fresh pair of buffers on the inlet and on the outlet. My question, if you use our Capillary 205 system, it has a huge capacity of the outer sampler, and therefore you can put there a lot of vials, closed vials with this buffer. So my question, if you prepare the buffer in advance and then you pipette them, aliquot them in different Eppendorf vials and put them closed inside the outer sampler, does it work in this case?
It does work. So I think Capel has 36 vials for inlet, if I recall correctly. So I did everything like that in Eppendorf vials, pre-pipetted, and all 36, well, excluding the injection vials. So it would not be 36 buffers.
Sure.
But they're all reproducible until the lid is opened. Once the lid is opened, the process started of evaporation, and then they don't work anymore. But yes, the only problem is it's limited to the number of vials. So I could not run my entire data set in just one load. It didn't work like that. So I had, because I have 3 replicates, and for each replicate, I need the buffer vial. So it took a lot of manual replenishment, but yes, it works with the closed vial. That's right.
Please keep in mind that for the inlet, we have not only 35 vials, but the entire, both carousels, the entire carousels, the so-called inlet, so-called internal carousel can be also used for the inlet vials. So altogether 59.
I have to admit, I wasn't aware that we could inject from outside.
Yes, consult Maxim or Artyom, they will explain you how to do this. So each position in both carousels can be used for the inlet. That means altogether 59 positions can be used for the inlet.
I understand. Yeah, that's good to know. That's good to know.
Okay, thank you very much. Thank you. Yeah.
Thank you.
Thank you, Vadim. Don't be shy, people. We've got some time, so go ahead and ask your questions. Just go ahead and ask.
Yes, please, Keba, I believe. Yeah.
Keba, okay. Thank you, Patrick, for that introduction of Lumex portfolio of instrument and the services that you guys, the great services you guys are doing all over the world.
You know us very
Emily,
well.
Thank you, Emily. That was a great presentation and great work. It's good to see, all the techniques, CE coming into the analysis of cannabis. For us, we are in the HPLC side. The question I have is, does the CE separate delta 8 and delta 9 THC? And then the follow-up question would be, because the gold standard, I believe, is HPLC when it comes to cannabinoid analysis. And I saw the work that you did in Dr. Harris's lab. There was a baseline drift. Don't know what the possible cause could have been with that, because it could be a gradient issue. For us, we have a method that it uses isocratic, and we don't see that kind of baseline drift.
For the first question, could you please? I'm just not. What was your question? If you
Yeah,
could...
the isomers like delta 8 and delta 9 THC.
Thank you.
Yeah.
That wasn't well, that wasn't the goal of our separation. I wouldn't be comfortable saying yes. I think it is possible with tweaking. This method, I don't know. I don't know. We didn't look at these isomers. I think it needs to be a separate method development, and I'm not. It would be difficult for me to answer.
Okay.
Yeah, I'm not sure. And regarding HPLC, we're using, well, we didn't do isocratic method. We did gradient.
Okay.
And the gradient was in presence of TFA. Let me just go back and slide. So the conditions were water as a solvent A with 0.1% TFA and methanol with TFA for B. So there is a linear gradient that I believe is causing the drift. But in case of fully isocratic method, I think we could. I just didn't see a lot of papers separating this specific set of cannabinoids, these 14. And we just wanted to separate, to just see, to compare with our method about the performance, which were quite similar, aside of the drift.
Yeah, for us, we did develop a method that separates, I think, 7 acid and 9 neutrals using isocratic. So we did manage to get, good separation. And it's a method that actually was developed by Restec. Restec developed it.
Restec,
yeah, if you go to their website, you might be able to see the method there. Yeah. So we did use isocratic. And then for your extraction, in our case, we use ethanol. And ethanol is very, really good in the extraction of the cannabinoids from plant material and also from the oils. But I see you guys use methanol. So I don't know how, the HPL. So I don't know whether that could have helped, or whether it would be good to know the comparison between methanol and ethanol.
The reason we used methanol is because we worked with Harris's lab. We inherited methods that were currently employed in their lab.
Okay, okay, got
Yeah,
it.
so I extracted and basically detected them, and I was happy with the result. I would assume now ethanol might perform better, but for the purpose of the method, that we were able to extract most. Actually, that might be a good point, that, for instance, the THCV and CBDV were not detected. Maybe they were not solubilized by methanol. That might be one of the reasons. That's just my guess.
The gradient was similar to what we use for HPLC, the acetonitride. So when I saw that, I said, "Oh, okay, that's quite, the solvent that you use for the the CE." Yeah, for our method, the gradient was, I think we use acetonitride. Yeah, water and acetonitride. For the isocratic that we use, it was water and acetonitride.
I would be interested in looking at the method for Restec.
Yeah.
Thanks, Keba.
Well, thank you.
I've got just before we jump in with Karen, because I saw your hand go up as well. There is Ilya Acer that was asking if the method and instrumentation is certified for analysis in the US. So I'll give you the quick answer to that. It's yes and no. Basically, the deal with this is that every state has their own regulations. So we kind of have to work with the people in a specific state and check their regulations. And then from there on, we can actually customize a method for them to use that would be okay to use by that state in that regulation. But I'm going to tell you right away, the gold standard right now is still HPLC. So it's still HPLC that's predominant. There's a couple of states, if I remember correctly, California, that in California, HPLC is kind of locked down. So there's really no other alternatives, but there's several other states that are a little bit more open and that might be able to use capillary electrophoresis as a a method to analyze the cannabinoids. Sorry, I keep slipping the tongue here on that word. Other than that, for the instrument itself, we actually have processes to validate the instruments and do an IQ, OQ on it. So that's the quick answer to that. Karen, and then I've got another question after that, but Karen, go ahead.
Thank you. Just quickly, Emil, why is the peak for the EOF in the Lumex information and in your paper so high? Like, is there something added to that in particular? It doesn't look so high in this, but in the like in your supplemental information and in the Capillary tech note, it's relatively high. Do you have any idea? Because you have sodium hydroxide in your buffer, which normally absorbs more than water, and like, I don't know, I'm mostly used to using phosphate buffers and borate buffers that don't absorb at all. And I know sodium hydroxide absorbs because you see the peak go up with 0.1 molar. This is obviously much smaller, but do you have any idea what is that just a phenomenon of injecting with methanol?
That was my guess.
Okay.
To be honest, I never paid that much attention to EOF. It was just a marker for me. But what my guess would be, it's the injection, because the injection plug composition is completely different from the buffer. So the moment it reaches the detector, I assumed that that's what gave the signal.
Yeah, I would have just expected a small, like a negative peak only, right? I'm just surprised that you see a positive peak on a sodium hydroxide. That's kind of quite theoretical, so it's fine. But your sample is, as you said, entirely in methanol, right? There's no water in it, yeah, to keep those in solution. Okay, thanks.
All right. The letters AA, so not sure about the name, but please go ahead and ask your question.
Thank you, Patrick, for the presentation, and also Emil. It's Aziza from SLP.
Oh, hi, Aziza.
Hi. So my question is about the buffer. So to just understand correctly, that you used the sodium hydroxide buffer?
I just use it as an electrolyte. It would not be buffering, but
Okay.
that's 6.5 millimolar sodium hydroxide would be my electrolyte.
Okay. My question: if we use another buffer are we gonna get the same migration time for every component, or it will be different?
I believe it will be different. Because if we use, let's say, triethylamine, even if we prepare it to the same pH and everything would be identical, it's still a different ion that has different mobility compared to sodium. So I would assume that separation would change. I can't predict in what way, but it would change. But I think that we could adapt our method for the buffering component, like triethylamine, play around with concentrations and pH a little bit, and I think we could achieve the same separation. I don't think it would translate one-to-one.
Yeah, because the result that you get when you compare the results for the capillary electrophoresis and the HPLC, you get similar results for each component, I guess.
Somewhat similar, different order, but similar in terms of quality of separation and the ease of quantification.
Okay,
the order
good.
is completely different though.
Yeah. Okay, so it's not the same order, it's different. Yeah, okay, great. And the last question is about you need to for each separation you need to have a new buffer, I guess.
That's right.
This is because we usually run different sample using the same buffer. Have you tried this one, and then you tried only one sample with one buffer and you get totally different results?
They're not totally different. You start to certain peaks stop separating. Like
Okay.
basically, it's the migration slowly becomes different and worse, and the separation becomes worse. It's not instantly. As you use it second time, it's not gonna separate at all. No, but
Yeah,
let's say you will
okay.
see instead of 14, 13 peaks because two of them will start to go migrate.
Okay, great. Thank you.
Great. Any more questions? Please don't hesitate. Karen, you're muted, dear, I think. Yes.
Thanks. Emil, did you ever try SDS at all? Like something different than beta cyclodextrin to help separate? Because you don't have are some of these isomers? Do you need the beta cyclodextrin for selectivity?
No, not for selectivity, because they
Yeah.
all separate in absence. It just takes
Right.
long.
Yeah.
Originally the way I tried to make the method was with SDS, because I assumed that the compounds are hydrophobic. So I would just start with micellar C, but I tried a few different classic buffers and SDS and just a few things, but it never got anywhere. Most of them did not separate very well, so I just did a different approach entirely.
Okay, thanks.
All right. Anything else? Okay, Emil, I think you're free now. So all right. So thank you so much, everyone, for joining the webinar. We greatly appreciate this. And it's kind of cool to have these nice discussions going on with actual real people that are actually doing real science instead of a slick salesperson. So nevertheless, thank you so much for joining, and we'll invite you to our next webinar. We're surely going to have a few more this year. So in the meantime, everyone, thank you again. Take care, and we'll talk to you soon. Bye.
Thank you. Bye.
Thank you.
Thank you. Bye.